So it is a pleasure to introduce Rocìo Isabel Paez, who will speak today about the resonant dynamics of Trojan exoplanets.
Thank you. Hello everyone, thanks for being here today. And as Alessandra said, I am going to talk about a paper that we recently submitted with Dr. That it is called Resonant Dynamics of Trojan Exoplanets 1. And it is one because we are planning to extend this work a little more. And this part in particular, it is called Overview of Resonance Structure and Diffusion. First, as a starting, I will briefly comment a little of the contents of my talk today. I will give the introduction as the motivation that we have for starting this study. And then I will pass to discuss a little of the formulation that we deal with. In particular, some hierarchical construction of the Hamiltonian that we have done, emphasizing some particular aspects of the Hamiltonian, and how we reach to compute new resonant proper elements. Afterwards, we correlate the formulation, this analytical formulation, with some numerical experiments, where we produce very nice phase portrait habitability maps, where we were able to analyze the influence of the mass parameter and eccentricities, and where we identify the corresponding web of resonances. And afterward, we proceed with a numerical computation of chaotic diffusion, where we were able to characterize different kinds of chaotic diffusion with different rates. And finally, I will close this with the conclusions of our paper. One remark that I would like to do here today is that even when the name of the paper is based on exoplanets, the formulation that we have done and the approach, it will apply to any kind of dynamical system. So it is able to apply for astrodynamical system in the solar system, for Trojan system of moons around a Trojan planet, and so on and so forth. So it's rather general. Well, I start. The motivation is, in 1995, two people, Mayor and Loss, found the first exoplanet around a solar-like star. It was more or less 20 years ago. And after that point, the development and discovery of many new exoplanets increased a lot. Up to this point, there are contabilized 3,000 exoplanets that were confirmed as true planets orbiting around stars, main sequence stars. And there are 2,000 more candidates for being confirmed as now. The problem of this, to find this kind of planets in order to, let's say, to find new sources of life, this is the key point of the discovery of new exoplanets, is that in general the method of observation of these planets are focusing in planets that are very big, like Jupiter or Saturn, and they are generally very close to the star, which is not very worthwhile for raising life, like in this planet as we know. So the key point here is, okay, these planets that we are discovering are useful in such a sense for finding life, or it is a problem. I mean, we know already that they cannot host life by itself, but they could generate something that could host life. And the answer to that question is yes. In 2003, in a paper of Menu and Trojan, they point out the hypothesis that they could be small planets, Earth-like planets, in the stability zones around the Lagrangian points L5 or L4, or also, let's say, as moons around these exoplanets. And after that, many different group of people were devoted to study if, well, first, these small planets were truly able to be formed in such locations or migrate to reach that point. If they were there, if we were able to detect them, so let's say we have the observational means by detecting these kind of planets. Or third, which is the question that we're interested in right now, is if these planets were there, are they stable enough for hosting life? Life needs some stability considerations. About the location of the planet, about the composition of the planet, and especially about how long it could remain there, because otherwise chaotic orbits or not very stable orbits are not able to generate the conditions that we need for life. And, well, so, considering the case that we are interested on, when this Trojan exoplanet is located in the liberation zone around the 4 and 5, is what gives us the motivation, for myself, to start working in this part of the dynamical studies. And, well, the mathematics. we have to introduce the problem that we are going to use. So the very first basic approach is to consider an elliptic restricted three-body problem. Here, in the first equation, we can see what is a characteristical Hamiltonian that describes this problem in a planar case, so we are not dealing with inclinations. Of course, we could say that it is not exactly the version we probably know about this Hamiltonian because the Keplerian part is not depending on mu and the starting function has three terms. But this rearrangement of the terms allows us to describe the system in modifiable variables that are not depending on the mass parameter. So mu is not included in the definitions of the new action that we are going to use, x and y. This allows us to describe all the system and to produce the numerical experiment, let's say, using the mass parameter explicitly as a parameter. Of course, the conjugated angles to the new action that we are going to introduce are lambda and omega, the mean longitude and the argument of the perihelion of the Trojan. And in such a terms, the Hamiltonian we have, it can be rewritten after this transformation when we have a 2 degrees of freedom system that also depends on another extra variable, which is lambda prime. Lambda prime is the mean motion of the primaries. All the quantities that have the prime are the quantities associated to the primary, that we could Jupiter, whatever we want, and the variables that are without the prime, that are just empty, they are associated to the Trojan exoplanet, or the Trojan asteroid, or anybody that is in a Trojan motion. Well, the first change that we introduce here is, since we want an autonomous system Hamiltonian, we have to extend a little the phase space, but including a dummy action called I3, which is conjugated to lambda prime. This Hamiltonian, in the way it is written here, is a 3 degrees of freedom Hamiltonian, autonomous. So it can allow us to keep trace of how the conservation of the energy is whole during all the integration that we can do in the numerical experiments. But up to this point, you could say, okay, you are still dealing with the elliptical restricted three-body problem, maybe in a more elegant and formal way, but it is the same problem. And the idea is to go a little further. So what we are going to do is we will add some additional effects. For instance, we can suppose that the ellipses on which the primary is moving is not a fixed ellipse, but it is precessing in time, which is something very characteristic in the solar system. And for instance, we are going to define that frequency of precession of the argument of the perihelion as G prime. And then, if we consider also additional planets, that it could be 1, 2, or S planets that are labeled here, this will also influence the primary on one hand, and directly the Trojan planet. And this can be written in a Hamiltonian. If we assume that the orbital elements of the primary, omega prime and epsilon prime, the argument of the perihelion, and the eccentricity of the primary, can be written like a little term called F, called phi, Rg, in the case of omega, and E0 prime plus F, which these J and F are harmonic functions of the frequencies of the let's say that are adding the planets that we add to our system. And we define associated action angle variables given by phi prime, which are exactly what appears above, and I prime or ij. We can recreate a much more complete Hamiltonian given by this expression, where we have to make an important remark. The structure of this new function R that we have here is exactly the same structure that it has here. Oops. This is having function in the elliptical restricted three-body problems, with the only difference that instead of dealing as omega prime with just a quantity, we live with the first approximation of omega, and instead of living with the eccentricity of the primary as just one quantity, we put it again with the leading term. Phi prime is a variable, this is a parameter. Well, this is our complete Hamiltonian. And what we are going to do in the rest of the development of the analytical part is to study a little this Hamiltonian to see what we conclude before the numerical experiments. Well, the first thing is, instead of considering the whole problem, go and focus ourselves in the problem that we have to study, which is the Trojan motions. So that means that we have to introduce some canonical conformations in order to focus our attention in some particular aspects. The first dynamical transformation that we use, we are replacing two angles. Instead of dealing with the mean longitude of the planet, of the Trojan planet, we are going to deal with the difference between the mean motions. Since we are dealing with a particular case of mean motion resonance, with commensurability 1 to 1, which is the Trojan case, well, this change of variables is rather logical. And also, we are going to add the difference between the argument of the perihelion of the exoplanet, of the Trojan exoplanet, sorry, and the leading term of the expansion of the Trojan of the argument of the perihelion of the primary. Well, if we compute the associated actions and we repeat the rest of the angles after the word, we can translate the Hamiltonian that I showed before in this long expression that we have here, which contains two parts. The first part that we are giving with an average, what in between is averaging the disturbing function over the only remaining short-term angle that is appearing, which is lambda prime. We recall that lambda prime is kind of analogy of the time of the system. It is the mean motion of the mean longitude of the primary. So we are averaging over this quantity, and we raise a new version, or a reduced version of the disturbing function, and the difference that we call R2. In considering these two terms, we have an average Hamiltonian and the rest of the Hamiltonian. If we focus a little in this Hamiltonian, first we can see that this Hamiltonian, considering what we have said before about R, is very similar to the Hamiltonian of the elliptic restricted three-body problem, but the only main difference is this term here, that what it is considering also the precession of the primary. So it is a kind of precessing planar elliptic restricted three-body problem, which depends on 2 degrees of freedom. And then we have considered all the secular effects adding with the rest of the planets in H1. Of this Hamiltonian, we can find the position of the force equilibrium that is going to be. That is going to be close to L4, but it's not going to be exactly L4 because we are not dealing with the circular case. So if we compute the equilibrium point, we can find that, of course, the variation in tau, which is the difference of the two mean longitudes, is P/3, 60 degrees. That the position of the semi-axis, which is given by the position of x0, is given exactly at the same semi-axis as the primary. But first, the value of the eccentricity is going to have a relation with, depending on the leading term of the eccentricity of the primary. And also, beta 0, the value of the variable beta for a fixed point, is pi/3. That means that if the orbit of the primary is precessing, I mean, not even considering the mean motion, which is a fast motion, but if the orbit is precessing, the position of the fixed point has to precess as well. So the difference is kept always up to 60 degrees. Since we found that point, we can move there. So we are going to redefine our Hamiltonian, but considering the translation in the quantities x and tau. So we call now the DLU. For the translation of the other two variables, the other conjugate pair that we have that was y, small y and beta, what we produce is that we are considering, let's say, beta was the angle associated with the action y. We are going to displace to the value of the fixed point and to describe the motion again as an action as an angle, given by the action y capital and phi. Okay, and now we have our map. If we rewrite the Hamiltonian, a full Hamiltonian, in these terms, we can split in several parts. And especially the first line is important one. The second line is giving the secular effects adding for other planets. So it's going to play some role, other if we consider a system with one primary and with more other planets. But the first line is only depending on what happens if we have a primary and let's say the Trojan. The splitting that we are doing is considering the terms of the disturbing function that are depending of lambda prime and phi only through the difference. There are several terms that shall depend only on these quantities, but also depends of the eccentricity of the primary. And the rest of the terms that will depend on these angles independently. To all this part here, we got the basic Hamiltonian. Why basic? Because if phi, let's say, is only appearing through this relation, that means that we can introduce a second canonical transformation and get rid of this one. So if we define a new angle phi f, the f holds for fast, and we keep phi like a phi p, the p holds for proper, we can redefine the Hamiltonian, only the basic Hamiltonians of the paragraph is underlined here in blue. And we can get, now an explicit 2 degrees of freedom Hamiltonian that depends on the pairs B and U, and phi and phi f, and yf, sorry, which is the coordinate path. Yp is appearing in the Hamiltonian, but since phi p is not appearing, yp is, strictly speaking, is an integral of motion. Okay, so if you keep track of how it is measured the motion here, so we have, let's say, this calibration with certain radius, the square root of minus 2y, capital Y, and angle phi. This is what this radius of this circulation around the fixed point is what the people commonly knows like proper eccentricity. And it is one of the considered proper elements that keeps track in a very accurate way, or the most accurate way as possible, that holds constant during, let's say, the evolution of the orbit. What we have found is in this description, exactly that definition keep track of two different variables that we can see here. So you see, y depends on yp and yf. And in our basic Hamiltonian, we know that yp is a constant of motion, properly speaking, but yf it is not. And actually, it follows fast changes in time. So, y, or let's say a function of y, is not truly a proper element since it's offering these variations that induce yf. Instead, if we define ep this way, the proper eccentricity this way, only considering yp, maybe it's not exactly the radius that I have shown before in the plot, but it's true reserved quantity. For sure, in the basic Hamiltonian, so here. But here also undergoes, if we produce the same canonical transformation, undergoes very slow variations. So it is still a nice proper element. Okay, in that basic Hamiltonian, if we can get track of the linear terms in y, we can find the associated frequencies of the system that are going to be fundamental for to finding the resonance that are involved in the system. For instance, if we want to compute the fast or the short-term motion, the frequency of the short-term motion, we found the derivative in terms of yf, and we can give an expansion that has more higher order terms, but at first order depends on mu, of course, and of the precession of the primary if n. And the same we will do with G, which is a secular way, how we define the secular frequency of the Trojan motion, that depends again of mu and J prime if n. If we get rid of the fast motion in this Hamiltonian, in HV, so we, let's say, average over the fast angle that remains in this case, we can find an average motion of this Hamiltonian that describes the synodic motion. So the libration around the libration for the fixed point. And we can also detect, but finding the equilibrium point of this track, defining the action associated that labels the invariant curves around this point, and to detect what is the frequency of that motion. That, of course, also depends on it. Since we kept track of these frequencies, we can define what is the most general kind of resonance by the resonant condition. Of course, this is the very, very general that involves, well, the three main frequencies that we have found, the frequency of the precession of the primaries, and any other characteristic frequency that will add any external planet. But, for sure, the resonances that are going to be important at this point are the resonances that are even present in the most of the basic and the most basic let's say, lecture that we can do from the system. This is the circular restrictive Friboni problem. So these resonances, what are involving is these two quantities. The frequency, the short-term frequency, and the synodic. If we consider the most relevant of those resonances are associated to the case where the integral with fast frequency is equal to 1, of course, which is the low order, and integers number for ns. And in particular, the resonant condition at false is we define n like, the negative of the integral number associated to omega s, this resonant condition. We call this resonance 1 to n, and this I say it now because in the notation, in the numerical experiments, we are going to use it a lot. And the rest of the resonance has involved, of course, the rest of the frequencies. In the particular case, when the first two, let's say MF and S and S, are greater than 0, we call it transverse, because we will see that all these resonance cause transversally, intersect transversally in the secondary resonances that are rather vertical. But when they are equal to 0, so they are just involving the secular frequencies, all the secular frequencies for a set of them, we call it for sure secular.
Yes. Sorry, why do you call secondary resonances, the previous one?
This one are the resonance that are appearing, the commensurability between the frequency of libration around the fixed point, yes, and the fast frequency that we had in this Hamiltonian. So what it appears is we have the fixed point that gives, let's say, the fixed point associated to L4, and we have a set of bifurcations that emanate from that point, and we will synthesize them. It's very clear in the numerical experiment. So for closing this part, maybe it's getting too long, we are going to make a lecture of how the planar elliptic repeating three-body problem looks like with this formulation. First, in this case, we are considering there is no other planet, that the primary is not precessing, that the eccentricity of the primary is a constant, and this allows us to deal directly with, instead of introducing the angle beta and the angle in the action B, to work directly with omega, the element of the continuum, and with the action X, as we define it at the beginning. And if we, let's say, proceed with the same canonical transformation, what we get is an expression of the elliptical Hamiltonian that depends on a function f0 and f1. The splitting between f0 and f1 is exactly the same. f0 is not depending on phi, and f1 is. But also, something to consider here is that f0 does not correspond to the circular case. And in the splitting that we are doing is not elliptical repeating problem as a perturbation of the circular case, but some terms that are depending on phi perturbating other terms that are depending on the eccentricity but not on phi. This allows, for instance, as I will do before, to introduce an average Hamiltonian, average of the fast frequency here, that it is 1 degree of freedom, that we can, well, 1 degree of freedom is integrable, but it is not the circular case. So we could represent a very, very nicely, or in a very accurate way, the elliptical case also. And first, well, as we did before, we could find the shift to respect to L4 in this case by, well, considering this term and expanding it to locate the equilibrium point that depends on the proper eccentricity that we defined before. Well, if we rewrite the Hamiltonian, we have the expression here, keeping track of what happens. Let's say we could find some anabolic oscillator in terms of the variable x and delta u, where delta u is no more than the distance to the fixed point of the variable u. And what we could conclude also before is that we, from u0, will bifurcate a periodic orbit, let's say associated to the integral numbers mf and n, that it will be 1, 6, 1, 7, these are the dot type cases. Every time that this expression holds true, when what we have here is our higher order terms in the eccentricities. Well, this gives more or less very fast landscape of how the system looks like. But I want to remark this thing, this splitting, because in this expression it is contained the justification of something that we are going to see in the future, in the next 20 future minutes, about the numerical experiments. So, well, the approach of the numerical experiment was always start with something that we know and as basic as possible, and to starting to the effects in order to produce something more realistic, but that we can still understand. And that means that we start with a parametric study problem, which is even a shorter and more, let's say, reduced problem to respect of the basic Hamiltonian when you consider F0. These are phase portraits, and here, for instance, we can see these secondary resonance that are emanating, that are the main ones that are dominating the dynamical space here. And we compute this considering, of course, we are integrating the circular attribution of degrees of freedom. The surface of section that we are considering is given by the pericenter crossing condition, which is defining a plane that it is passing through the apocenter and the pericenter of the instant orbit of the Trojan planet. And we, so what it means, pericenter and apocenter, that the radial velocity is equal to 0. And it is pericenter if the radial acceleration is positive. So this gives us the points that we want to keep for constructing the surface of section. And afterwards, the initial conditions for integrating those orbits are given in a line that connects delta U recall in the distance in the variable 2 to respect to the fixed point. And well, the quantity x, the variable x, is measured along a line with a slope p. This is this way because, for instance, I am showing here two of the results for the 1 to 6 secondary resonance and the 1 to 7. And it is clear that for odd resonance or even resonances, the symmetry is different. So if we have defined just the line, the horizontal line, let's say x equal to 0. In the 1 to 6 works perfectly because we are plotting exactly the middle of the stability island. But in the 1 to 7 hits the separatrix in one of the stable points. So we are not going to see any of the orbits that are inside the stability island. So to keep track of the slope gives us, let's say, a most accurate visualization of the phase portrait. And then, the cases that we study are, of course, different bifurcation for different values of mu at very first order. So we change the value of mu, 100 values of mu between 0.001, which is a little greater than the value of Jupiter in the case of the solar system, up to 0.01, which is a little value of mu in general, and 35 initial conditions in u from 0, in delta u, from 0 to 1. With this, we can, and for a value of the proper eccentricity, not the eccentricity of the Fermat, but the proper one that we define as a proper element, equal to 0. This gives this, let's say, column of plots, 100 of them. And with them, we can keep track what are the best values of mu for recognizing the different secondary resonance that will appear. We choose some of them that were represented very well, the resonance that are, let's say, within this range, that goes from the 1 to 12 up to the 1 to 5, which is the limit that you can find. And for those values of mu, we also produce the same phase portrait, but with bigger values of the proper eccentricity. So this is, for instance, 0.06, 0.01, and the same for the other value of mu that we consider for the 1 to 7, which is 0.031. The first main result that we can have here is, as long as we increase the proper eccentricity, first, the position of the resonance is going outwards, and it's farther and farther of the fixed point. And second, the islands of stability are increasing. Up to a certain point, that the last KM tori that is surrounding this structure, that doesn't mean that this is truly the last KM tori, breaks. So we start, the chaos is entering, the chaotic domain that is all around is entering and involving this resonance up to the point that only we track of just, let's say, a small remainder of what was the stability island before. But the inner part, the very inner part that was, let's say, surrounded by the secondary resonance, more or less keeps the same structure, doesn't change much. And these features calls for all the values of mu that we consider. If we want to improve eccentricity, so we have an circular term, a mathematical one. This is a four-dimensional plot, and we can see that this representation of the system is not going to be good. So we have to change the tool. Use the tool. What we are going to use is a chaotic indicator like light that I think we all know, but it is a very fast and a way of categorize regular orbits from chaotic orbits. And what we do for preparing these maps, in order to understand the dynamical features of the system, is to take the same line of initial conditions that we use for the phase portraits, to take 400 initial conditions in delta U along that line, to integrate for 1,000 periods with a time step of 1/300 period, and to make a line associate the initial conditions to a certain color bar that is given for that line. And then to increase a little the proper eccentricity. And we do the same again. And again and again. And we complete the whole line of 400 different values of the proper eccentricity. This completes this mass. Okay, so what we see is exactly this line. So if we read here, what we found in this section is the 1-to-6 resonance in this case. And then we have the rest of the stability domain up to the border of the chaotic form. But this way of representing, for instance, allows us to detect higher order resonance, secondary resonance, because we see are, for instance, the 7 minus 43, 0, so it is not any mistake with that resonance frequency, sorry. In both, it's a higher order, much higher order resonance, secondary resonance, that in this phase portrait are impossible to see. They are too small. And also, we can plot how they depend of the parameter of the proper eccentricity, how they increase, how they expand, how they move outwards, as we were predicting for the phase portraits, as long as it increases. And, of course, the key point is to see how it changes when we add some eccentricity to the primary. The main feature is, here we will not have resonance that involve the secular frequencies because they are not present. But here we have, and this scheme here, it is not dominating as it was before, let's say for higher orders of EP, for these higher order secondary resonances, but it is completely filled by this transversal, the one that we call transversal resonances before. Of course, there are appearing some other transversal resonances in the inner part of the plot, but this structure here is going to dominate a lot the stability of the whole region in this part of the plot. We keep track, of course, of what happens with the 1-to-6 resonance, but for instance, we can see, sorry, this is a typo, it's the eccentricity 0.06. But the 1-to-6 resonance here, it decreases a lot the size of the stability Iceland. It is more or less negligible. And for higher values, it's even worse, it disappears completely. But also, all this structure here disappears for higher values of it. When you have seen some results of many papers about how the increasement of the eccentricity of the primary shrinks a lot the size of the stability domain, is because this effect. This part, the exterior part, is not changing, it's not affecting much. But all this resonant structure that we have here is the one that disappears, and this is why it shrinks a lot. Well, these F-line maps that we produce for the selection of the frequencies allows us to show, for instance, in this case, the 1-to-6 resonance for more values of the eccentricity of the E prime. Up to the point that I see, I mean, here there is no track of resonance in that part of the plot. Yes?
No, I wasn't reading
the values, yeah.
Okay.
And this thing was done for the 8 resonances that we consider, the 1-to-5 up to 1-to-12, for 2 or 3 different values of mu associated to them, in order to distinguish what was the best for representing the system. And, well, for instance, here we have it for 1-to-7. The features are more or less the same. You see some, many transversal resonances that are, sorry, not here, many transversal resonances that are disappearing at the point that for a higher value of eccentricity we will have none. And the thing that only remains are few transversal resonances that are appearing in this part of the stability domain that we call non-resonant, because it has a clear lack of resonance with respect to the rest of the resonant domain. Also, another feature is that this, as long as the centricity is increasing, these transversal resonances are appearing, let's say, for higher values of EP and going down in this direction. So we see next to the 1 to 7, we have the 1 minus 7, 1, of course, because the third frequency that it is here is very small, so the orbit cannot be very far from the one that is trapped in the secondary resonance. If we increase the value, are appearing the older associated resonance of the multiplets, so it is, let's say, 1 minus 7, 2, minus 7, 3, that are going down and disappearing inside the chaotic domain as far as the prime increases. And this plot does shows something very similar to what we have seen up to this point. The main difference was, instead of fixing mu and change consider different values of the proper eccentricity and to change the eccentricity, now the older parameter that we are changing is mu. So what we can find here is, let's say, the 400 values of mu that we consider, again the 400 values of the proper vibration. And what we can see here is exactly the same. We are plotting the same, but this is depicting very well the different bifurcations of resonance that we can find. So we can see, for instance, this is the 1 to 6 resonance because it is bifurcating about 0.004 in the value of mu. That is, well, it's very different to see, very difficult to see from far, but it can be seen that this resonance has 2 layers corresponding to the 2 sides of the separatrix. And for instance, 1 to 5, the one which is here, has only 1. This is about the slope that we consider here. The slope has to be the same for all the variables, so it is 0. So one of here, like a single, let's say, layer resonance, and the other like double layer resonance. But first we can see that, of course, for higher values of mu, the bifurcation is less and less often, but the size of the resonance is bigger and bigger. So the influence of this resonance is much bigger than these ones. We have the 1 to 5, 1 to 6, 1 to 7, 1 to 8, 1 to 9, and more of that. Here the bifurcation is much more often, for sure. It's more frequent. The influence is smaller. But since they are very horizontal, the slopes of this resonance in this plane is very horizontal. That means that the presence of this resonance is highly depending on the value of mu. Very close values of mu will give that you have stability domain dominated by one resonance or not completely. So this plot represents very well that idea.
Please, can you recall me the meaning of the abscissa?
Delta U.
Delta U is?
The distance
between?
From the fixed point up to the initial condition that we are considering in delta U. Is, sorry, different.
Okay, where the coordinates there are?
Is U and X, the conjugate pair. X is the non variable associated to the semi-axis.
Yeah.
And U is in terms of somehow the mean longitude. Actually, transformation after transformation over the mean longitude.
The center is one of the Lagrangian points, right?
Sorry?
The center is one of the Lagrangian points, right?
Kind of. Is exactly the Lagrangian point. We are talking about the circular case, but since it is not, actually it is moving around that. The shifting that I presented before, I say that U0 was presenting a shifting to respect L4 is exactly that, how it differs, the difference between this fixed point and exactly mathematically speaking L4. So, well, more or less, we have an idea how in the space of parameters, how this resonance looks like, on which parameter depend, if they increase or not, or if they, and how they change if we change the physical parameters of the system. So we want to see what happens to the stability.
Can I ask something? Sure. In your system, you have the same information like in the restricted white column, but the main point is stable up to some value of eccentricity of the primaries?
Yes.
Is it exactly the same? Because you have the other frequency of the precision, and does this affect the problem or not?
No, yes, of course. I mean, the linear stability of the Lagrangian points are depending on mu, always. But we are dealing with much smaller values of mu.
So you don't.
The maximum value of mu that we consider is 0.01, and I think the one that we need for the Roche criterion, that is what you're saying, is 0.03 or something of the order of magnitude 0.1.
But it depends also on the centricity of the primaries?
The stability of the point, yes, but we are not dealing with values anymore. Actually, some people will say that the range of eccentricity that we consider maybe is too small for talking about exoplanets, because exoplanets has a very wide range of eccentricities. But since we are focusing on exoplanets that could host life, we could not have a planet of an eccentricity of 0.2, because it may reside in the habitable zone for a while, but after some time it's going to be outside. So this is how we more or less we bound the values of the
it was in
planet.
the seminar delivered by Eric on the CERN.
And, well, let's talk about stability. So we say, okay, let's go keep track of what happened if we have some initial condition and we let involve a lot in time. This part is regular. I mean, it's going to be there, it's not going to happen, it's bounded, nothing is going to happen. This part is the most interesting, because at very close to resonances, it will be exactly one of the chaotic layers of the resonance, and we want to see what is going on. So here I am showing the results of a very small experiment that consists in taking, with some certain parameters, but the same always, two very close initial conditions, where the only difference resides in the value of the delta U, from the distance with respect to the fixed point, in such a way that the green orbit is, let's say, in the chaotic layer of the 1 minus 6, 1 resonance, and the black orbit, it is in the layer of the secondary resonance. And we integrate for exactly the same time. The green orbit, the only thing that does is jumping from one side to the other of that resonance. All the time. Doesn't do anything else. This variation that you can see here, that you can say, okay, but in diffusing, I mean, your supposed proper element is changing somehow, but okay, this difference it is inside this variation that we will have when we consider, for instance, the term f1 of the starting function in our model. So it is allowed. I mean, this thing is not truly diffusing. But
it's confined.
Yeah.
The diffusion is confined.
Or if it is not confined, it's such a slow diffusion that we will not measure in 10 to the 5 periods of the time. The other one, I don't know if with the light is possible to see, it's stuck here and jump here, which is the other layer of the secondary resonances. Jump, but in some moment it starts jumping to other resonances. And goes and returns, and goes and returns, and goes and returns. I think this orbit in particular was not escaping for this orbit, for this integration, but I have evidence of other orbits that were doing something very similar and escaping afterwards in this order of magnitude of time. So what's going on? Why one is doing this thing and the other one is doing something essentially different? Well, this is why I remarked the Hamiltonian at the beginning. We have a split, a Hamiltonian that was depending on the eccentricity, so it was not circular, but it was not depending on this angle that we call phi, or phi 2, because it's associated with the proper quantity. But the second term that was, let's say, important in the Hamiltonian was f1, it was the starting function, the part of the Victorian function that we call f1, that was depending on phi. What this term does on the first term of the Hamiltonian is a pulsation. It's a pulsation with a frequency of this angle, of phi, which is that we call G when we found the frequency for our problem. So the structure that we see is more or less what we have seen in the phase portraits, but pulsating. It moves from one place to the other. So what we have is, in these cases, the pulsation holds, I mean, it's true, exists, but it doesn't have any influence because this resonance doesn't have many nearby resonances. But in this part of the plot, that we have a lot of resonance very close one to the other, this pulsation produces an overlapping of pulsating regimes. So it allows the orbit to escape of one of the resonance and being trapped on the other one and do it for instance. Here we can see it. In blue here, and in purple, red, and in green, in this plot, we have exactly the same orbit in the circular case and in elliptical case. The parameters are exactly the same orbit, the same quantities. Here it is an orbit that is completely confined in a very close to separatrix, but in an elevation orbit inside the stability Iceland of the secondary resonance. Here, since the whole structure is pulsating, this orbit, in the same time that the blue orbit is doing this here, is evolving. The first integration, I think, up to 10 to the 3 periods of the primary is the purple points. Up to 10 to the 4 is the green. Up to 10 to the 5 is the red. And here, if you can see, reach more or less 0.8, 0.7 of the propagation quantity. So it is jumping a lot. And if you can see, okay, but maybe what does it mean? How we can see more evidence of that? We can analyze the eccentricity, the proper eccentricity. EP0, it is the commonly defined proper eccentricity, these radians that I showed before, and EP is our proper eccentricity. In the circular case, EP0 holds some certain variations, but it is somehow bounded in certain, or have a very characteristic mean value, or proper eccentricity is exactly an integral function.
And the reaction of the exponent for the orbit is positive or it is equal to zero?
I don't recall to have computed. Okay. For sure I computed, but I don't recall the number.
Okay.
I will check. But what we could see is that what happens in the elliptical case of the two proper eccentricities is that there present sudden jumps, like changing the mean value, which is associated, let's say, to a different resonance that is visiting at that point. And we can see here that EP, though now is truly changing, it has these fast variations that we were explaining before, changes less than the other. And the jumps that it produces are a little, let's say, smaller.
But they have the same behavior, right?
Sorry?
They have the same behavior. I mean, if you see the
Yes.
main feature is the same.
Yes, but it is actually, well, for sure the fast variations are induced because for phi, for this pulsation that we will have. The additional terms that we will have, the red with respect to the black, are due to this action that we define YF. This is the reason, but the behavior has to be somehow similar. Well, the last part is I'm closing here. Let's make some statistics about what is going on in this resonant region of the stability domain. We take an ensemble of orbits in this square. This square is a section of the slide maps that I showed before that are going from 0.33 up to 0.93 in the propagation, and from 0 to 0.06. So you see, we are representing very well this whole distribution full of resonances. And we're integrating and producing a snapshot of what is going on with the orbits in 5 different intervals from 10 to the 3, 10 to the 4, to the 5, to the 6, to the 7 periods of the planet. It's a rather long integration. And after every integration, we are contabilizing all the orbits that are here, that are 60 and 60 in each of the axes. Then we are considering if they are regular, escaping, or transition orbits.
According to the color?
The color is a representation, according to this criteria we have here.
Because in the FLI there is no green.
No green, no.
So,
No, exactly. This classification is half and half independent of the FLI. Independent because, well, depends in the sense that for computing regular orbits, what we are considering is that the FLI, this one is here in time after the end of the integration, if it is lower than this quantity, and if the amount of periods of the, let's say, of every step of integration we are using over 10, Well, if F line, let's say, holds to be lower than this, means that it is regular, because we know that the behavior for regular orbit of F line is linear. So this is, let's say, a rather strict bound, but if the orbit holds to with this condition, it's truly regular. I mean, we can say it is regular, and actually we stop integrating the orbit at that point because it's not going to produce anything new. On the other hand, and this is the independence with respect to the fly, we are considering that the orbit is escaping if the cumulative error in the energy, and this is why we produce the autonomous Hamiltonian, present as very sudden shock. The integrator that we use is not symplectic, so this accumulative error is increasing on time. See, we can see this are pure, that is accumulating. In 4,000 integrations, or integrations of the system time steps, that it is more or less about 1,000 periods of the primaries, and even more, we can see that the increasement of this quantity of the order of 10 to the minus 9. This orbit in blue here, and in purple here is the same. So this curve corresponds more or less up to here of the purple curve. What happens is that when the orbit escapes, truly escapes, goes out of the stability domain, the jump is much bigger than this accumulated error. And we were testing different scales. And this amount, this difference in the value of the cumulative error of the energy represents very well when it is truly escaping. And this is the paradox independent of the fly. So, sorry. After every snapshot, what we get is the statistics about how many of the orbits are regular and in position and escaping. Well, we can see here in the table the results. We can see, for instance, of the orbit that we considered regular at the beginning, it is not, let's say, a big difference in respect of the final number of regular orbits. So this, according to our criteria, this things was rather okay. We can make it very well in regular orbits. The transition orbit at the beginning are a lot, and the bigger group. Then they decrease a lot, up to having 600 more or less. And the scales, the step after step of the scales that are represented, well, certainly, I will show you the distribution.
Maybe later.
There are two slides more.
I imagine.
Well, here we present the results in a more graphical way. On top, we have the distribution of the energy, of the logarithm of the energies, for the blue orbit that are transition orbits and the red that are escaping. Here we have the values of left lines, a distribution in terms of left line. And in the lower panels, what we have is a histogram with the amount of orbits, of blue orbits, only transition orbits, with respect to the value of left line. And this is for the first interval of integration, which is 10 to the 3, 4, 5, 6, and here in the example we have the 7, which is the last one. The first thing that we can notice is that this line here, horizontal line that is increasing, you see, in every time step, is the limit that gives the integrator, the cumulative error of the integration. Because this accumulated naturally just for using this numerical method. At the beginning, we have some blue orbits that has a higher value with respect to this threshold, but after we continue integrating, these orbits are disappearing, so they become all of them escaping. But then, we can see, at the beginning, most of the blue orbits are accumulating here, or here. This shows better. But as long as we continue integrating, this, beside the orbit that are escaping, we have another peak of the distribution here. This orbit has a very high value of F'. 50 was in order to avoid overflows, 50 was the maximum value of F' that we could use. So if the orbit has 50 or higher value, it's truncated at 50. So this orbit has a very high value of F', but yet, they are not accomplishing the escaping criteria. They are still stuck somehow in the system. And we can see that even after the end of integration, this number is not small. It's more about 200, it's about 200 orbits of a total of 3,600. It's an interesting number. That, of course, well, these things here are regular orbits that somehow fail in the criteria of being regular. but the increasement is very, let's say, very according to the regular behavior and the accumulated energy due to integration and not to the escape of diffusion or whatever. But this one is probably one of the most interesting aspects of this experiment because it gives an idea that there are many sticky orbits, and orbits that are dynamically rather chaotic according to the value of the light, but they are not escaping anymore, so they are still stuck in the system. We can see very quickly how the distribution of the escaping times, this is an histogram, is totalizing the logarithm of the amount of orbit that escapes according, well, with respect to the time, and the time is measured in the amount of period of the primary that we consider. Here it is 100 periods of the primary, 1,000, 10,000, and so on. And we can see that this distribution has clearly two peaks, it's very important, and we have fast escapes that occurs around the 1,000 periods of the orbit, and a second one that occurs 2 orders of magnitude later. This was something that we were not expecting. The decay of this sort, of this peak, we feed a power block, it's a power block because it's a logarithmic scale, with an exponent of more or less 0.8, which is very characteristic of the sticky behavior, of the stable chaos behavior. And we were expecting just one peak. To find 2 peaks was very interesting. But it makes us want to understand which part of the system is evolving in this way and which part of the system is evolving in this way. So what we did finally, with this I will close, is to correlate the escaping times and the flight mass that gives to ourselves the structure of the system. Well, here in the flight map, as we computed before, only restricting ourselves to the section where we take the ensemble of orbits. And what we have here is, well, the 3,600 orbits, and in color scale, that it is trying to emulate the flight, but gives a different information. In very yellow, in the lightest yellow that we have, correspond to the orbit that escaped in lower time than the 3 periods of the primary. Up to, let's say, the darker red, all this part of the color scale, correspond to escaping orbits for different time scales. Let's say up to 10 to the 4 periods of the primary, 10 to the 5, 10 to the 6, 10 to the 7. And these are in brown, red, and darker yellow. In light purple, that I don't know if you can distinguish, but it is more or less this zone here, we have the transition orbit that remains transition up to during the whole integration. That they were never accomplishing the criteria of being regular, but they were never escaping. And in darker purple, it is a regular orbit. The first thing that we can see here is that the escaping times are very well correlated to the flight maps, to the structure. We were not expecting such a good correlation. That the fast escapes, let's say all this region here and this region here, correspond to the truly chaotic region that we are considering in the ensembles. That the layers of the resonance that we can have, even a little bit secondary, but for sure the transversals, are the ones that are given, let's say, the lower escapes, 10 plus 5, the orbital were taken to 10 plus 5, and this part here is given the sticky zone. And this part here corresponds exactly to all this region that we call resonant domain of the stability domain, that it is full with the transverse resonances. 10 to the 7 periods of the primaries is not a short time, I mean, for orbit that has a very high value of left line, that are relatively high in chaotic. So if we could even have some, let's say, extrasolar Trojan planets located here, that these bodies will not escape, or not, they don't have to escape necessarily before this time. So when we consider the stability zone, we have to include these zones at least with some criteria, because they are not truly escaping orbits, fast escaping orbits. And, well, sorry for keeping you long, it's 1 hour of talking, so I will give the conclusions very quickly to close here. Just to resume a little what we have shown today. First, We produce a Hamiltonian formalism based in modified dynamic variables that allows us first to consider to include secular effects due to one or more planets, even when the numerical experiments were not considering this. This is one of the extensions of the problem, to repeat some numerical experiments considering truly more planets, not only the formulation. And also allows us to develop a hierarchy of the Hamiltonian, where the basic Hamiltonian is not exactly the circular case, it's a little more complex, but much more rich dynamically speaking. And for sure to develop some new resonant proper elements that are working nicely even in resonant cases. To find the frequencies and for sure the characterization of resonances. And we could study this new formulation in some numerical experiments based on the elliptic reflective body problem through phase portraits and F-like maps, depending if we are considering the circular case or the elliptical case. And also to measure and produce statistics of the escaping times of the orbit when we are dealing in particular with resonant cases located in the transversal resonant domain. We found that there are different paradigms of chaotic diffusion according to which resonant orbit is belonging. And the statistical study of the ensemble of orbits gives us main result that escaping times have a bimodal distribution, and that there is a very good correlation between the escaping time, the plot of the escaping times, and the F-like map that allows us to recognize which part of the system is within one or the other behavior. And that's it.
So thank you for Vergata's presentation. And questions? Yes, I have a question which is, do you see whether there are some applications also to astrodynamics or the concepts
we are talking, as I say a little at the beginning, we are talking about exoplanets because it was a motivation. But the truth is that this would represent perfectly the solar system. And to consider the Trojan as Jupiter in probably a much more efficient way, like considering just the elliptical or the circular reflective problems. The formulation that we reach is not difficult. The truth is not difficult. I was impressed that it would be relatively easy to develop even the complete Hamiltonian. And so it can be truly translated even to the Jovian case, when you have Saturn and the system of moons of Saturn. Applicabilities there are many. It depends on the problem that we are interested in studying, of course. And for sure, if we do not do the sequence of canonical transformation that we did, and we just kept the complete Hamiltonian, we can study any system. I mean, any system that is including these effects, of course. So we can study moons, we can study the influence of S+1 planets, and it's rather general. So it's very interesting.
Okay, so I think we can stop here now. Thank you. Thanks a lot.